Hi, I want to do a problem today involving angular impulse and momentum. But before we get into that problem, I want to spend just a moment or two looking at the background of the idea of angular impulse and momentum. And by way of doing that, I've set up a body here so that it has a particular angular acceleration, alpha, and it also has a linear acceleration, a. And those are kind of drawn there with respect to the center of gravity. Now, when it comes to the idea of angular impulse and momentum, it is most useful if we can express these things in terms of angular impulse and momentum around some other point that isn't necessarily the center of gravity. So I have this other point P that's listed out here. And to get started with kind of the theory of how to do these angular impulse and momentum problems, let's start with what we know. We know that Newton's second law for the case of angular kind of stuff is expressed this way, where we sum up all of the moments here, and we're going to do that about point P. Those are all vector terms. This is going to be equal to a couple of things. One is the moment of inertia around the center of gravity times alpha, where alpha is a vector quantity, plus, and you might remember we had this other term of r, g with respect to p, or g relative to p, crossed into the mass times the acceleration of the center of gravity. Okay, and that would also be a vector term. And what that second part right there was called, that's called the kind of the kinetic moment that happens if you're trying to sum moments around some point that is not the center of gravity. Well, to kind of introduce this idea of angular impulse and momentum, what we're going to do is take the integral of both sides of this expression. So I'm going to take the integral over here with respect to t. And we'll do that from one time to another time. And we'll do the same thing on the right side. We'll take the integral over there of all of that stuff, dt. Okay. And also that goes from one time to another time. Okay, just like we saw with linear impulse and momentum, we have a term over here. This is an angular impulse. And notice here, I'm going to actually put another note here. This is about point P. Okay, so it is kind of dependent on what point we take it around. All right. What happens with the other stuff over here? Well, let me actually kind of, start that down here. What happens when you take the integral of all of that? Well, moment of inertia is not generally something that is time dependent, and so that kind of just comes out, and so you end up integrating over time this idea of angular acceleration. Similar idea over here, you're integrating over time this quantity of r g cross p, g with respect to p crossed into m times the acceleration of the center of gravity. So what happens here is you end up with basically a difference, right? You have a difference between the moment of inertia around g times omega, okay? Because when you take the time integral of angular acceleration, you get angular velocity. Okay. For this other part, we're going to get r of g relative to p crossed into the mass times the velocity of the center of gravity. Okay. Now I'm going to put subscripts on all of these. So because we're going to take the difference between one time and another, I'm going to say this is at the end of the time interval noted on that integral right there. And I'll do that for a bunch of these. This is, where you end up with there. This is where you end up with here, right? You end up with your final velocity there, and so on and so forth. Okay? So then you take that and you subtract where you started. Okay, as in like an initial ig times omega 1. Okay, and you'd also subtract kind of your initial state with respect to this velocity as well. Oh, that should be a 1. Okay, so this down here, let me kind of put all this in a box. This comes from this term up here, and what it indicates is this is a change in angular momentum. Okay, if you look at just like one of these terms, you know, like up here, this is the angular momentum that you have at the end of applying the angular impulse. Okay, so let me kind of take a moment and just say that that is one of your you know, angular momentums. Okay. Now, I should probably go back and talk a little bit more about angular impulse. What can cause angular impulse? Well, I'll kind of indicate a couple of things. One is if you apply some sort of a concentrated moment onto this thing in some way, you know, and that can be around any old point. It doesn't matter what point you're talking about when you talk about a concentrated moment or even a set of them. Here we've got the sum of all of these, right? So you could have as many of those as you wanted. That can be one thing that causes a moment applied around point P. You can also have things like forces, like I could have a force applied like this, right? That force, because its line of action does not pass through P, that force would create a moment around point P, and so that would also have to be taken into account for our angular impulse about point P. Okay? Anyway, another couple things I should probably draw on here is that, you know, this alpha leads to an omega, and those are two different things, right? That omega being the angular velocity that results from the change in angular momentum. There can also be a different velocity that happens, doesn't have to be in the same direction as A. So, you know, it can be in any old direction. I'll just draw it on there in some arbitrary direction. All right, so I know this doesn't do a whole lot for us just yet. It's kind of difficult to see how this would be applied just based on this amount of description here. So we'll do an example in just a moment. Before I get to the example, though, I want to do one other sort of bit of background here, and that is a special case where we have fixed axis rotation. This is a very important case because this happens quite a bit, and I wanted to kind of talk through this just for a moment. When you have fixed axis rotation, it is common to have it set up so that you can have maybe a torque around that axis, or maybe even, you know, some forces that would be applied somehow onto this thing that would be rotating around the axis. Either way, we have a little bit of simplification that can happen if we know that this is around a fixed axis, and it has to do with the moment of inertia. So when you have this situation, your angular impulse term doesn't change, right? You still have an integral from one time to another of the sum of all of the moments, but this time we're going to specify that all of these moments are taken with respect to that rotation axis, and then, you know, with respect to time. Okay, so that part really didn't change much. Only thing we did there is just make sure we're specifying that it's with respect to that axis. On the other side, though, it can change a little bit because it is often possible for us to find a moment of inertia that is around a specific axis. And so I'm actually going to label that I-axis, you know, meaning that that's, again, a moment of inertia with respect to that axis. That times the difference in your omegas, that gives you your change in angular momentum. Okay, and so why is this important? Okay, well, this is important because if you take this moment of inertia, and you're very careful to take that moment of inertia around that axis, it saves you the effort of having to do things like cross products where the center of gravity, you know, let's say the center of gravity of this thing might be around here, you know, you would have to actually take into account the linear velocity of that center of gravity, and that would be included in the expression that we gave just a second ago for angular momentum. Whereas if you take this moment of inertia specifically about the axis of rotation, then that takes care of that without needing to have an extra term in there. And that's definitely going to come up in the example problem that we work. And so we're going to start that right now. Okay, so here's the example problem that we want to work. Let me kind of talk through it just a little bit. We have a motor that is going to drive this assembly of two different rods, okay? So the motor is going to apply this torque that is given with this expression, this function up here. And so as it applies that torque, the little assembly there is going to be picking up speed because of that torque that is being applied. Now it starts with an initial speed of 10 radians per second, and you know, then it's going to have that torque applied. We're given some information here. Initially, this string constrains rod 2 so that it's in a position that's perpendicular to rod 1. And rod 1 is just welded onto the motor shaft. Okay, we're given some other information here. We know the weight of rod 1 is 5 pounds. The weight of rod 2 is 2 pounds. The shaft and rotor of the motor weighs 1 pound, and it has a radius of gyration of 3 inches. Okay, so then what we're told here is that after the torque has been applied, that's this torque function over here, after it's been applied for 6 seconds, the string is going to break. And then rod 2 is going to swing out, and once it swings out, it will lock into a position such that rod 1 and rod 2 are actually collinear with one another. Okay, now here's what we're supposed to do. First of all, we're supposed to find the angular velocity that the assembly reaches at the instant before the string breaks, and then, as another problem, you know, another part of the problem, find what that angular velocity is the instant after the string breaks and the rod locks into its new position relative to rod 1. For the purposes of this problem, we're going to ignore the finite period of time that it would actually take rod 2 to swing out to that position. It will happen very, very, very quickly, but I should note that it won't happen necessarily instantaneously, but we are going to treat it as if it does happen instantaneously, even though we know that it doesn't. So, but that's just an approximation that we're going to make. Okay, so those are the two of the angular velocities that we want to find. The next thing we want to do is find how much energy may have been lost when it swings out. So it's going to be a non-conservative kind of a movement that happens, because when that rod goes out and locks into place, that kind of constitutes a collision, and so that can dissipate energy. We're going to figure out just how much energy got lost by the assembly when that rod 2 swung out and locked into its new position. And then for the last part, we want to find, you know, it's kind of another thing that begins to happen. Let's say that as soon as it locks into place in its new position, we shut off the motor right at that point in time, and then apply a brake pad of some kind to the shaft surface, okay? And the shaft is 1 inch in diameter. So we'll kind of apply a brake pad to the surface of the shaft and push on it with some normal force. And we want to find what normal force would we need to push on it with so that we get it to slow down and stop within 8 seconds. So we'll find an 8-second slowdown, how much force we would need on that brake in order to get it to slow down like that. All right. So there's a number of things that we need to do here. Why don't we start with this? There's a few just sort of basic things that we should probably do. First of all, we are given the masses of rod 1 and rod 2 as numbers in pounds, okay? We kind of think of those as weight, but those weights all indicate a particular number of pounds mass. So it's important for us here to go in and actually do some conversions and get those masses converted down into something that's a little more easy for us to deal with, which would be slugs. So for instance, let's start with rod 1. It weighs 5 pounds, okay? So the mass of rod 1 is just going to be equal to 5 pounds. Now, we know that there are 32.2 pounds in a slug, okay? Which basically means I wrote that wrong right there. We should put slug in the numerator and 32.2 pounds there in the denominator, okay? So let me just punch that in real quick. 5 divided by 32.2. All right, so 0.1553 slugs. Okay, what about the mass of rod 2? Okay, it'll be the same deal except for rod 2, let's see, weighs 2 pounds, so not really different. All right, we'll just put in 2 divided by 32.2. Okay, 0.06211. Okay, and that's again 2 pounds times a slug per 32.2 pounds. Okay, and we have one other one that we should probably do, and that is the mass of the rotor and shaft, I'll just call that M sub R, associated with the motor. And for those of you who aren't really familiar with motors, inside of this motor is going to be a rotor that actually has things like wire and magnetic surfaces that are inside of there. Anyway, we'll just say that we know that the mass of all that is going to be equal to 1 pound. Okay, and again we'll multiply that by a slug per 32.2 pounds. Okay, and that gives me 0.03106. All right. Good so far. All right, so now what we want to do, there's a kind of a central part of this problem, and it is, it kind of goes back to the fixed axis rotation discussion that I did just a minute ago. When you have fixed axis rotation, it is very convenient to express the moment of inertia with respect to that axis, okay? And so what we want to do next is find these moments of inertia for each of the pieces so that we can come up with an overall moment of inertia. Now here's the thing, we actually need to do this for 2 different positions, right? There's actually 2 different positions that we're going to have for rod 1 and rod 2. So I'll tell you what we'll start with here. We'll start with finding, I'll actually just subscript these with 1 and 2. So when I say 1, that means before the string broke, okay? And that moment of inertia that I have, and maybe I'll also put here that this is about the axis, okay? And do that for part 1, all right? That moment of inertia comes from a few different places. So for one thing, there's the moment of inertia of just the shaft and rotor. Since we are given a radius of gyration, that's actually a fairly easy calculation to do. We just would have 0.03106 slugs, okay, times the radius of gyration squared. So that radius of gyration is 3 inches. Okay, so that part, it's just K. K is that radius of gyration, so K squared times M, and you get your moment of inertia contribution from just the shaft and rotor part of it. All right, the next part comes from rod 1. All right, rod 1, one of the nice things you can do there is, if you look it up in the table, which I will skip doing right now, hopefully you take my word for it, that it gives you, one of the formulas is 1/3 of the mass of that rod, the mass of that rod being 0.1553. slugs times the length of that rod squared. And the length of that rod is 9 inches. Okay, and that would be squared. And again, this is 1/3 instead of 1/12. We get used to using the 1/12 version. That's the version where you find it about the CG of the rod. If you want it about one end of the rod, then it ends up being 1/3 instead of 1/12, but everything else ends up being the same. All right, so now we've taken care of the shaft and rotor. We've taken care of rod 1. Now what we need to do is add on the effect of rod 2. Now we don't have anything that's nice and clean just yet for rod 2, so what we need to do is express it in terms of the moment of inertia for rod 2 about its own CG, and add to that a parallel axis theorem component. Okay, so to do that, we will add 1/12 of the mass of rod 2. The mass of rod 2 is 0.6211 slugs. Okay, and then we're going to take the length of that rod squared, so it'd be 4 inches squared. All right, and to this we need to add, okay, remember you take the mass of that part of it, which is 0.06211 slugs, and multiply it by the radius squared from the CG of rod 2 to the axis we're taking this about, okay? And so that basically would be a line. I'll just sketch right on here. There's a line that goes like to the middle of this rod. And the length of that line is just going to be equal to the square root of the length of rod 1 squared plus half of rod 2 squared, okay? So maybe I'll put that in here like this. This is just going to be equal to the square root of 9 squared plus, okay, 4 inches over 2 squared. And then all of that is squared because of the parallel axis theorem part of it. All right, one other thing that I'm going to do here is that, you know, ultimately, I think this would actually be more convenient if I could express it in terms of slug feet squared. So if I take all of this, I can multiply it by a conversion factor to go from the square inches that I have here to square feet. Okay, so to do that, I'll have foot squared per, or I could actually just do foot per 12 inches and square all of that. Okay. All right, so that is the calculation that I need to do now. So I'm going to punch them in here. All right. 0.03106 times 3 squared plus 0.1553 times 9 squared, okay, over 3, minus, not minus, plus, okay, 0.06211 times 4 squared over 12 plus 0.06211 times, okay, here I'm taking the squared of a square root, so let me just put in here, okay, what's inside the square root, and that would be 9 squared plus, okay, 4 over 2 would be 2, so that'd be 2 squared. All right, and I'll just go ahead and hit equals, and to this value here, I will apply my conversion, right? So 1 over 12 squared. So I take this and I divide it by 144. Okay, and that gives me a 0.06829 or so, 0.06829. and that would be in slug feet squared. So now what we want to do is come in here and do it again, but now for the position where the rod has now swung out and locked into position. Okay. Now here's the thing, not much actually changes. Okay, so because not much actually changes, I'm going to copy this, paste it right here, and we'll just change the things that really need to change. So first of all, I'll say nothing changes with our radius of gyration and mass of the kind of the rotor and shaft. Nothing changes with respect to rod 1. Okay. Again, actually nothing changes with respect to the moment of inertia for rod 2 about its own CG. The only thing that really changes here, again, doesn't actually change the mass of rod 2, but the one thing that does change here is this radius. Okay, and now instead of that radius being the that value that we just found, we now have a radius that is rod 1's length plus half of rod 2's length. So it'd be 9 inches plus half of 4 inches. It'd be 11 inches here. Okay, so let me do this. I forgot to store this. Let me just store that into A, and then I'll go ahead and calculate what comes out of this other one. Okay. So I may as well go up here and start editing this. What we found there was that it's going to be 11 inches, and that should be squared. Oops. Like that. Okay. When I hit equals, it gives you this value, and then we'll divide that by 144. So this ends up giving us 0.08382. Make sure I wrote that correctly. 0.8382 slug feet squared. Okay. All right, and let me store that into B. That's just some background stuff. We're just going to need that, and so I'm just going to go ahead and get that taken care of there first thing. Now let's get into the meat of the problem. All right, one of the things that we do need to find here is just how much impulse is applied as a result of this torque function applied from 0 seconds to 6 seconds. And so let's go ahead and do that part here. Okay. Angular impulse. Okay, this is going to be equal to the integral from 0 to 6 seconds of 7 foot-pounds sine of t over seconds, okay, plus 3 foot-pounds per second times t dt. All right, and there actually isn't that much that we need to do with this before we go ahead and plug it in to our nice little calculator that we've got. All right, so we'll just go ahead and plug it right in here. We have 7. Oh, actually there is one thing we do need to do. Keep in mind that anytime you are using one of these functions, like a sine function like this, it's good for you to have your calculator in radian mode in order for it to work properly. So I'm going to go in here and put this into radian mode, and then we'll punch this in. 7 times the sine of x. Okay, the over seconds just handles the units. Okay, so that part doesn't necessarily need to be dealt with specially. plus 3 times x. Okay, and this goes from 0 to 6. All right. And what that gives me here is 54.279. And let's think about what these units would be. This would actually be foot-pound seconds. Okay. That is the angular impulse that is applied over those 6 seconds. Well, what do I do with that? Well, this is the change in the angular momentum. So that means that the angular momentum, and h is one of the variables that's often used for this, so I'll just go ahead and use that. H at the instant before the string breaks. It was instant before string breaks is going to be equal to the amount of angular momentum that I had at the very beginning plus my angular impulse. Okay, and so let's go ahead and start calculating these. Okay, because what we're trying to figure out first is just what is this angular momentum that I have at the instant before it breaks. From that value, I will be able to calculate my angular velocity. So I'll get to that, but first we'll do it this way. So this is going to be equal to the I that I have about my axis there, which was 0.06829. That would be in slug feet squared times that initial angular velocity that I started out with, which was 10 radians per second. And to this, I'm going to add 54.279 foot-pound seconds. Okay. Now let's actually spend a moment and think about these units here for just a second. Okay. So here we're talking about, let me actually work from this end, a foot-pound second. This would actually be a foot times, and a pound is a slug foot per second squared, and here we have seconds. Okay. So what happens here is we have slug feet squared per second, because this seconds cancels one of these seconds. Okay, so I have slug feet squared per second. What do I have over here? Slug feet squared, radian doesn't count, per second. So these are actually consistent units here, just making sure that we're, not screwing that up. Okay, so here our angular momentum that we have, again, at the instant before the string breaks. Is just going to be equal to these things calculated. And I believe that I actually had, so I have that as, the value. Tell you what, I can't remember if I stored that, so let me store that into C. And just kind of keeping track here. This is in C. I believe this was in A, and this was in B. All right. So at the instant before break, we basically just have C plus 10 times A. Okay. And this gives me 54.962 okay, and that's just going to again be in slug feet squared per second. Well, what can I actually do with that angular momentum? Well, there's actually a bunch of stuff I can do with it. The first thing is I can recognize that at the instant before break, I still have the basic equation here that my angular momentum is going to be equal to I omega. Okay, it's kind of my basic equation. And so because I know that omega is h over I. Okay, so that means omega, again at that instant before the string breaks, is just going to be equal to h over I, which is 54.962, okay, slug foot squared per second, divided by 0.06829 slug feet squared. All right. Let me actually take this. I don't think I've stored this value yet, so let me store this into D. Okay, and so I'll take D and divide it by A. Okay, which gives me 804. All right, that would be in radians per second. 804.7 actually. Okay, and so that's actually the first part of the first question, is what is that angular velocity that we achieve the instant, right before the string breaks. Okay. All right, well, what's next? What about the angular velocity right after? Well, here's the thing. If we're talking about the instant before and the instant after, and we're talking about basically zero time in between, there has not been any chance for there to be any angular momentum to be transferred into or out of the system. We have conservation of angular momentum. Okay, so this h at the instant before the break is actually equal to h at the instant after the break. Okay, energy is not conserved in that process because of the collision that happens when the rods bang outward, but in this case our angular momentum is conserved because there's been no time for there to be any impulse applied. Okay, and so what we do to figure out the speed at the instant after the break, or at the instant of locking straight, because that's what happens with those two rods. At the instant of locking those two things straight, it's really just going to be equal to that angular momentum, still the same value, 54.962 slug foot squared per second. Okay. but now dividing it by this other moment of inertia, because now we have a different moment of inertia that suddenly happens right there. And so we'll divide this by 0.08382 slug feet squared. Okay. So that gives me D divided by B, which could be 655 point, we'll say 655.7. radians per second. Alrighty, so that actually covers, these two answers right here cover the first part of the problem. Okay, it asked you to find the angular velocity of the assembly at the instant before and after the string breaks, more or less. Part B. Okay, Part B says find the amount of energy lost in the assembly due to this shift in position of rod 2. Okay, well that isn't actually that hard, because we know how to compute the amount of energy in a rotating system, a system that rotates around, a system that rotates around a, hopefully that moves. Yeah, we'll have to do some of this manually here. All right. So change in energy, kinetic energy, is going to be equal to 1/2 of our final energy minus our initial energy. Well, the 1/2 is in there for both terms, so I'll just put it out here, but it's going to be 1/2 I omega squared. Okay, now we have two different I's and we have two different omegas for before and after the string broke. So we'll do the final first, right? So there our I value is 0.08382. Okay, slug feet squared. Oh, and that's actually going to be multiplied by that omega that we have there at the final, 655.7 radians per second. Okay, minus the initial. Okay, and the initial is going to be 0.06829 slug feet. Okay, and that gets multiplied by the initial angular speed. This is actually the angular speed right before the string breaks, which is going to be 804.7. radians per second, that squared. Okay. Now what we should find here is that we actually have a negative change in my kinetic energy. Okay, why should it be negative? We'll make sure that it is whenever we calculate it here. We should find that it's negative because we lose energy whenever that collision happens where the rods snap out. You know, that can't necessarily give us energy, so we should see it losing energy. All right, so I believe I had B there times 655.7 squared, all right, minus A times 804.7 squared. Okay. And so I end up losing there 4,092.76. Okay. Now let's think about what these units would actually be here. Okay, so this would be, you know, 1/2 of all these. This is actually slug feet squared, okay, per second squared, it looks like, is what one of these terms winds up being. A slug foot per second squared times feet, okay, this is pound times feet. And so this ends up giving us foot-pounds. All right, so that is my change in energy right there. So the fact that it turns out negative, that is the loss, right? That's the fact that there's a loss there, is that negative, and then that's the value. All right, part C. At the instant after rod 2 locks into its new position, motor torque is shut off, and a brake pad with a kinetic coefficient of friction of 0.4 is applied to the shaft surface. So kind of imagine a little brake pad coming in here, maybe, you know, right here, that's about to push into the surface, and you start pushing on it with a normal force here on that surface, trying to slow it down. Okay, and the question is, how hard would you have to push in order to stop this whole assembly in 8 seconds? All right, so how do we figure that out? All right, well, first of all, let's actually kind of sketch this from above now. All right, now we have one of these rods. It sticks out like this, and there's another one locked so that it's right like this. Okay, we happen to know what the moment of inertia is around the axis of this thing. Okay, and what we're doing here is we're pushing a block of material into the surface here with a force of Fn. Okay, and this thing has, you know, maybe a angular velocity like so. Well, if the angular velocity is like that, then we're going to be reacting with a force at this surface of Fn times mu sub k. Okay, and then that gets multiplied by the radius away from the center to give us a torque. Okay, so maybe I'll just say that we're going to have a torque that's applied here that's going to be equal to Fn times mu sub k, which is 0.4, times the radius, okay, and the radius is going to be 1/2 an inch. All right, now that's torque. If we want to consider impulse, angular impulse actually gets easier when you have a constant torque. That's one of the reasons I do this. Is kind of two things I want to point out here. First of all, you can have a force rather than a torque that is what's causing this, and you just take that force times the perpendicular distance to the axis around which rotation is happening, and that's what gives you the torque. Now what you can do is multiply by time, right? So here we have Fn times 0.4 times that radius of 1/2 an inch times, and we want to do this within 8 seconds. Okay, and so the only question is, how much momentum must this bleed off, right? And the answer to that is all of that momentum that happened either before or after the string broke, either way, that is the amount. So 54.962 slug feet squared per second is going to be equal to that force that I have to push with times 0.4 times 0.5 inches times 8 seconds. Okay, now something to be careful with here, I probably need to convert this inches into feet. So something like that, so that it ends up with consistent units across both sides of this expression. All right, so there's all of that stuff. I believe I had 54.962 stored into D. Okay, so let me go ahead and use that. I'll take that and I'll divide it by 0.4 times 0.5 times 8. All right, and actually the 12 that I have down here ends up being in the numerator up here. Okay, and that means I need to push with about 412. That's my normal force here. 412.2. Let's think about the units on here. So we have slug feet squared per second. Okay. Here I've got, this ends up being in feet, so that knocks out one of those feet, and then I have seconds. That goes in the denominator, so we end up with slug feet per second squared, which is just a pound. And that's the normal force that we need to apply in order to get the thing to slow down within 8 seconds and slow down to a stop. All right, let me actually kind of recap this problem to make sure that we're okay with it. I worked this problem in a MathCAD sheet, and so let me actually go, I'll put room right here and talk about it right here. Okay, talk about this chart a little bit. All right, so what happens here? Kind of recap what happened with the problem. First thing is, we start with this little torque function, right? So this is that function, you know, that happens from 0 up to 6 seconds. That's this little function right here. Okay, makes sense because you got that little waviness from the sine plus a little kind of linear portion, goes up like that. Then the string breaks. Okay, now what happens with speed during that portion? Well, first of all, note that we have a small amount of initial velocity right here. You notice that that doesn't go actually all the way down to 0. That's that 10 radians per second that we start with. Then, due to the torque, it increases in speed, and the waviness even here kind of makes sense because you have the largest amount of torque right here. That's the highest amount of slope of the speed right here. Okay, then you drop down the amount of torque, you have the lowest amount of slope right there, and then finally you stop applying torque, and that's where you stop gaining speed. All right, well then what happens? Well, the string breaks, and what you see happen here is that that little drop right there, that's what happens due to that angular momentum being conserved, but the I changing, the moment of inertia changing, and so it causes that instantaneous drop in angular speed because of that string breaking. Then what you have is the torque drops, and instead of being 0, we now have this resistive torque due to the braking. And that resistive torque causes the speed to bleed off until you get back down to 0. Okay, so if you wanted to actually track what the speed was of this thing, it would have a shape that looked just like that. Well, I hope this has been a useful video. If it has, please subscribe. Always appreciate comments if you have questions about it. And definitely appreciate likes too. Helps me know that I'm doing something that's helpful. I hope you have a wonderful day, and I'll see you later.